So a couple of classes ago, we were introduced to what's a tangent and what's a secant line. And a secant line is choosing any 2 points on a graph and drawing a line through them. And a tangent line is taking any 1 point on the graph and drawing a line at it. So that's the main difference. And we looked at this, if we pull up this example that we had with distance from Winnipeg, what we were doing when we were finding the average rate of change over a certain period of time was like taking 2 of those points, drawing dots on them, and drawing a secant line. And the slope of that line was an average rate of change. Now, a tangent line would touch a point only at one place. So if we look at the diagram, we have maybe, oh, computer's happy with me today. There we go. So what we're imagining here is maybe this is part of a parabola, okay? So I have a parabola like this, and I have a specific point right here. And at that specific point, I could draw a tangent line like that. And if I find out the slope of that tangent line at that specific point, I will find out the instantaneous rate of change. How fast is the parabola getting steeper at that point? And the way that we figure that out is we start by considering that point and another point, and we start with a secant line. Right now, would you agree that the secant line and the tangent line have different slopes? Okay, it looks like the secant line is steeper than the tangent line. And if I analyze this diagram in depth a little bit closer, just looking at the 2 red dots that I've drawn, what I have is I have a point A and a point B. And initially, what we're going to say is the x-coordinate at point A is A. The x-coordinate at point B is x. So the y-coordinate, depending on the function, would be f of A at A and f of x at x. And if we look at the horizontal distance between those 2 points, it would just be x minus A. And if we look at the vertical distance between those 2 points, it would be f of x minus f of A. And you know from grade 10 math that the slope of any line is rise over run. So we've got that in this box here. We can say that the slope is f of x minus f of A over x minus A. Now, if I took this red line and said, I'm going to make my second point closer, are the slopes the same? No. But are they closer than what they were before? Yes. Okay. So I'm like, all right, well, what happens if I take this point and move it even closer? It's getting better and better and better. So what we're going to try to do, and here's Formula 1 for getting the tangent, is we are going to imagine that our value of x gets closer and closer to A. And it makes a limit. And we would say, when they're exactly the same, they should equal the slope of the tangent line. But the problem with them being exactly the same is if I plug in A for x, I'm dividing by 0, and that's not allowed. So it's the same kind of issues that we've been working on with our limit questions as we go along. So what does this look like? Okay? We have a parabola here, 3x squared minus 6x plus 1. It has the point 2, 1 on that parabola. So in our situation, in this case, the a value is 2. We know that that's the point that we want to stay fixed, and that's the point we want to find the slope of the tangent from. So when we go to the formula that we were just introduced to, the slope of any line is the rise over run, and we're going to look at the limit as x gets close to 2, because that's the value we want to find it at. And then, according to the formula, it's f of x minus f of a over x minus a. But in this case, our a value is 2. So we take the original function, 3x squared minus 6x plus 1. We plug in 2 into the equation for a, and we come up with the following equation. Can we evaluate this limit right now? No. What's the problem? We're dividing by 0. So we don't know the value of the limit because we're dividing by 0. But if we multiply everything out, this whole thing becomes minus 1. That nicely simplifies with the plus 1. And then you would just be left with a 3x squared minus 6x. Can you see that that can be factored? You could pull out a common factor of 3x, which is really good because this is what we're aiming to do, is we're aiming to have two factors that are identical that can simplify away, especially since if they can simplify away what's causing us to divide by 0, then we can evaluate the limit. So notice we write the word limit just like the format from before. We have to write limit all the way through until we can plug it in. Here we can plug it in. So now we know that at the point 2, 1, the slope is equal to 6. So our new formula helped us figure out our slope. The question was asking us to find the equation, find the slope of the tangent and the equation of the tangent line. So we've done the first part. We have found the slope of the line, and we know a point because the place where the tangent touches it, that point 2, 1 will also be on the line. So now we go back to a review of grade 10. If you want to find an equation of a line and you know the slope and you know the point, do you remember how to find that equation of a line? Okay? And there's sort of two common methods. How many people first think about y equals mx plus b? Okay? Usually by grade 12, that's the first thing you would think of. If you thought of y equals mx plus b, you know m is 6, and since you know the point is 2, 1, you could plug in 2 for x and 1 for y, and then you've got an equation where all you have to solve for is b. I thought it said the equation after, and the equation, or is yours different? Maybe sometimes I change them on here, and no, you just stopped reading. Okay, that happens. Okay. All right, we're good. So from here, you could figure out quite easily that b is equal to minus 11, and so we have our equation y equals 6x minus 11. Do you guys remember the point slope form of the line from grade 10? That's this equation. Y minus y1 equals mx minus x1. If you don't remember it, well, then you'd probably go towards method on the right, y equals mx plus b. This one, do you remember your slope formula? Rise over run. Okay? Can you see that the point slope formula is really just your slope formula rearranged? What do? They just move this up to the other side, and instead of having 2 points, an x2 and an x1 and a y2 and a y1, they just replaced one of the points with just x and y. So those two formulas are very, very much related. The nice thing about the point slope formula is you plug in your slope, you plug in your point, same thing you would have done here, but instead of solving for b, you just need to rearrange the equation to get y equals mx plus b. So for each of these, I'll remind you of both formulas for finding an equation. But at this point, you're back to grade 10. So what does this mean graphically? Is everybody done writing this? What this means is that if you graphed 3x squared plus 6x plus 1, that'd be a parabola that's opening up. On this graph, it has the point 2, 1. And if I drew a tangent line at that point, okay, the slope of this tangent line is equal to 6. And if we put this blue thing on a graph that said distance from Winnipeg and hours, this steepness of this line would mean at hour 2, when x is equal to 2, if you looked at your speedometer, you would be going, whatever, 6 kilometers per hour. Pretty slow. Not a crazy speed. But that would be an instantaneous rate of change. And if we were talking about distance and time, that would be the speed that you were going at that moment. So we've done one together. I'd like you to try one on your own. Another parabola. Just to make sure we're on the same page. Were you able to plug things in correctly? Simplify it, the 3's cancel out, and then it factors nicely so that your x minus 1's cancel out. So if you're working on this and nothing factors out for you to cancel out, it's sort of an indication that you probably did some mental math or little algebraic error somewhere. In a question like this x minus 1 needs to cancel out. And then once it cancels out, then you can apply the limit and get a slope of 4. And now that you've got that slope of 4, can you find the equation of the tangent line? Because now we have the slope, which is 4, and we have a point. We have the point 1, 3. So again, I have both methods. If you like the y equals mx plus b method, because it's easiest to remember that formula, then you'd plug in your slope, plug in your point, find the value of b, and you get y equals 4x minus 1. Or if you like the point slope form, y minus y1 equals mx minus x1. Plug everything in, rearrange it, you get exactly the same formula or the same equation. And we are so close to calculus and derivatives right now. Now, another way of doing the same thing, and the reason we're going to do it another way is this is even closer to calculus and what Newton thought, is we take that same parabola, we take the point A just like we had before, and we take the point B, but instead of calling the point B x, like we did last time, this time we say, let's measure this distance as h. And I don't know who decided that h would be the perfect letter to use, because what do you think of when you think of h? Height. And this is a length. So, yep, you can shake your head. Maybe h was not the best. But would you agree, if this point is a, this is f of a, and if this length is h, then this value is a plus h, and the value of the function is f of, if you plugged in a plus h. So this is exactly the same idea as the last time, but I think some of the notation is a little bit more confusing, because before you just had x and f of x, and you had f of x minus f of a. But the same thing, we could create a formula for the slope of the secant, and now what do we need to happen in order for the secant line to be the same as the tangent line? We need this h to get smaller and smaller and smaller. So the way that this formula looks at, here's our secant line, and then here is our new tangent line formula. So Ted, what you just missed is, I'll do a quick explanation again. We did the same thing, but instead of using x here, we called this length h. And so if this is the point A, and you went h to the right, this would be the point A plus h. And you have the same idea of rise over run, and you would get a different formula for the slope of the tangent line. And for those of you that have already studied some calculus, this formula is much closer to the derivative formula that you know. Yes? Close. It's not quite, because it still has the a involved. And it's still specific to tangent lines at a specific point. As soon as you replace the a with an x, a general point, then it becomes Newton's quotient. So the difference here is we get questions like we had before. Find the equation of the tangent line to this curve at the point 3, 5. We still have that the value of a is 3. Whereas with Newton's quotient, you would find an equation for the derivative and then be able to apply any point to that. So according to the new formula, you would have the limit as h goes to 0. Since the a value is 3, you'd have f of 3 plus h minus f of 3, all divided by h. My h is a little stubby there. Make it less n-like. What's the problem? We're dividing by 0, just like last time, dividing by 0 as well. Now, with this one, you have to be really good at your function notation. What does f of 3 plus h mean? Well, if f of x is x squared minus 4, now you would replace wherever there were x's with 3 plus h. So we would get 3 plus h squared minus 4 minus f of 3, 3 squared minus 4. Can you see a shortcut here that this part here is given to you by the point? You wouldn't actually have to calculate that. You're wasting a little bit of time plugging it in. But they tell you you have the point 3, 5. So f of 3 is 5 without having to replug it in. That could have saved us time on the questions before as well. What do we have to be careful with? How do you square 3 plus h? Make sure that you get 9 plus 6h plus h squared. And once again, just like in the last formula, what we want to do is we want to rearrange things. We want to simplify. Here, the 9 and minus 9 cancel out. We have a common factor of an h, and we get to this point once it's factored that we can simplify the h. That's our goal, because we're no longer having a problem of plugging in 0 for h. And that means you can plug in 0, and we get our slope is 6. So we have our slope is 6. We have our point at 3, 5. And you can find the equation of the tangent by either using y equals mx plus b. Yes? In this case, this formula for m is specific to the point because of the value a. So you don't have to say it's at 3 because you've kind of implied that by using that formula. Okay? Once we get to the definition of the derivative, the next idea, these formulas we won't use because the definition will be much more powerful. So if you use y equals mx plus b, plug in your point and your slope, you get b is negative 13. Or if you use y minus y1 equals m times x minus x1, you get the same formula. Y is 6x minus 13. I'd like you to try the next one on your own. It has a square root. So it's a little bit more challenging. We've just done parabola after parabola after parabola. And they've been fairly straightforward. Put up that the slope is 1/6. I won't show any of the work, so you can at least see if you're on the right track at that point. I know most of you have got it already, but I will show the work here so you can see the process At this point, the 9's will cancel out, and then you have h divided by h. Those will simplify to just be 1, and you can apply the limit, plugging in 0 for h and getting 1/6 for the slope.